Hello everyone. Today I would like to introduce the application of eigenvalues and eigenvectors in science and engineering. I will divide it into three parts. The first is an introduction, and the second is 4 applications, analysis of 4 fields, and the third is a summary and outlook. So now let's take a look at the first part, introduction. Eigenvalues and eigenvectors are beyond pure mathematics. They are the key bridge connecting abstract mathematical logic with engineering and practice and natural science exploration. Besides, let's look at Ax equals to lambda x, this equation. So in this equation, A means square matrix, and X means eigenvectors. Lambda means a constant, also mean as eigenvalue. So when a linear transformation acts on a normal vector space, most vectors change direction. However, eigenvectors only stretches or reverse in length. And the eigenvalues are the key coefficients describing the magnitude of this change. So, leveraging the fixed direction of eigenvectors, we decompose complex systems into independent components, enabling efficient dimensionality reduction, model analysis, and key feature extraction. So these are how to solve the eigenvalues and eigenvectors. So first, we can list the characteristic equation that A minus lambda I equals to 0. So we can find all possible eigenvalues. And for every eigenvalues, we can use this formula to find the correct eigenvectors. So these are about how to solve it. Now let us move to the core of this presentation, the classic and far-reaching applications of eigenvalue theory across 4 different fields of engineering and science. The first application is mechanical vibration analysis. Every structure around us, like bridges, buildings, and machinery, all possesses inherent vibration characteristic determined by their material and geometry. Uncontrolled vibration over time will lead to material fatigue and ultimately catastrophic failure if left unaddressed. In this field, eigenvalues equals to natural frequency. It means that the system naturally oscillates without external forces. And eigenvectors equals to mode shape. It describes the specific deformation pattern. So while this is very important, it is because the resonance. So when the frequency of an external excitation forces matches the system's natural frequency, also called as eigenvalue, the resonance occurs. This phenomenon will pushing stress far beyond design limits and posing severe threats to structure. One of the classic cases is Tacoma Narrows Bridge, which occurred 1940. This is an image of it. So this is because the aerodynamic elasticity was ignored. So it is lead to this destroyed. It is a very important engineering warning. So even today, engineers rely on eigenvalue decomposition to avoid resonance risk. It is truly the lifeline of civil and mechanical engineering. So this image is a 2 example about the resonance. First is bridge vibration. So using this formula written on here, the workers will calculate this to get the eigenvalues, also called as natural frequency, to avoid the resonance. So this is a mode shape of the bridge. And the next example is a spring mass system. Also, it has eigenvalues, also called as natural frequency, and eigenvalue, eigenvectors, mode shape, and resonance. So these are the first application. Now let's take a look at the application 2, Google PageRank. Before Google, early search engines mostly rank web pages by keyword matching and the number of incoming links. PageRank, however, stands as one of the most influential and practical applications of eigenvector analysis in information technology, revolutionizing how we retrieve relevant information from the web. Its core idea is that to let the World Wide Web as abstracted as a directed graph, where each page is a node. So a page's importance is determined by two factors. First is the quantity of incoming links. The other is the quality of the page's linking to it. And after that, we can construct a link matrix M, where Mij represents a link from J to I. The PageRank score factor R, also known as the eigenvector of the matrix M, can be calculated from this equation. And the eigenvalue lambda is equals to 1. So in other words, we simulate a process where a user randomly clicks links indefinitely. After an infinite number of jumps, the probability of the user staying on each page will be stable. So the stable probability distribution is the principal eigenvector of the matrix, which is also known as the PageRank score of the web page. So its core advantage is that the results are objective and stable. So this is an example of the Google PageRank. So in this example, obviously the ID equals to 1. This has the 0.304, so it is the highest importance. And the ID 6 is only 0.045, so it has the lowest importance. So this is application 2, Google PageRank. Now let's take a look at the application 3, image processing and face recognition through principal component analysis theory. Principal component analysis, also known as PCA, it relies on the eigenvalue decomposition of the covariance matrix to transform high-dimensional image data into a more compact representation, retaining critical visual information while discarding negligible details. So one of the examples is digital images, which are high-dimensional data structures, where the junket pixels exhibit significant redundancy and noise. PCA solves this problem perfectly, and its core is the eigenvalue decomposition of the covariance matrix. In the covariance matrix, the eigenvectors represent the principal directions of feature variation, while the eigenvalues quantify the amount of information contained in each direction. So in this image, it shows the workflow of the PCA. First, it will collect the image dataset, and next, it will compute the covariance matrix. And next is to solve the eigenvalue decomposition, and through this, it will solve for the eigenvalues lambda and eigenvectors x. And next, we will select principal components. So in this step, we will choose the top k components from the n. So it achieves the dimensions reduction from n to k. And the next step is feature extraction. So the project faces images into face space. This is also a dimension reduction step to let the face images into space. And the last step is to face recognition, compare feature factors using distance. Up to now, all the steps of the PCA has done. And by the way, the PCA theory also has a wide range of applications, like image compression, face recognition, smart security, and image retrieval. So this is the application 3, image processing and face recognition of PCA. Now let's take a look at application 4, the stability analysis of automated control. So this is a short background. The eigenvalue theory is indispensable in autonomous driving, aircraft flight control, industrial robotic manipulation, and aerospace navigation systems, ensuring these complex systems operate reliably in dynamic environments. So for these complex systems, can be described by the state space mode, this mode. So the dynamic behavior and stability are entirely governed by the eigenvalue of the system matrix A. So no external inputs can alter the stability determined by the eigenvalues. From this, we can know that the eigenvalue is the only factors affect the stability. And here are 3 states. First is Re lambda, negative. It means it is stable. All states converge, no sustained oscillations. And the next is Re lambda, positive, unstable. It means system states diverge exponentially, leading to loss of control. And the last is Re lambda, equals to 0. It means marginally stable. It means it is neither converge nor diverge. Next is an image to show it more clearly. So in this region, it is stable region. In this region, it is unstable region. So obviously, it is only determined by the lambda's first number. If it is positive, here, positive 1, so it means it is in this region. If it is negative minus 0, then it means it is in this region, stable region. And in this line, means it is equal to 0, and it means it is marginally stable. So this is application 4, automatic control. Now let's make a short summary about why are eigenvalues so important. So from the 4 applications before, we can note that first is simplifying complex systems. It decomposes coupled systems into independent eigenmodes, which greatly reducing modeling difficulty. And the second is it's improving computational efficiency. It reduces simulation load and optimizes resource allocation. And the third is rapidly judging system stability. It can quickly determine stability of mechanical or control systems. And the last is supporting interdisciplinary frontier development. It serves as the mathematical foundation for AI, machine learning, big data analysis, driving modern technology innovation. And here is the outlook about the future power mathematics. Eigenvalues and eigenvectors. They are core tools with both theoretical and engineering values. They have permitted modern technology from image processing to big data dimensionality reduction. And here are the new opportunities in frontier fields. In quantum computing, eigenvalues help us to solve complex quantum systems, energy level, and state equations. In deep learning, eigenvalues analysis plays a key role in neural network optimization analysis. And in complex network analysis, we can use eigenvalues to discover key nodes in social and biological networks. From classic engineering to future technology, eigenvalues and eigenvectors will continue to serve as indispensable mathematical support, fueling future engineering design, scientific research, and intelligent technological innovation. That's all for my presentation. Thanks for listening.